We're going to cover the chapter 2 of our book, which is phase behavior. And the motivation, as we discussed before, is since the oil and gas is our product, we need to know its behavior, and we need to know how this product reacts at different pressure and temperatures, at what conditions it's stable, and all the other information regarding to that. And in order to study properties of petroleum, gas, and liquid, we need to understand the relationship between different phases, because we can have the oil and gas in the gas phase, in the liquid phase. We can have them both in gas and liquid. And in some special cases, like in hydrates, we can have it in a gas and solid solution, like the gas and water mixing and generating the hydrate clusters. But before going to that, we just need to make sure that we understand the basic definitions of the some terms that we are going to use, like pressure, temperature, and volume. What do we mean by those? What is the physical meaning of these parameters? And as we start, we are going to always start with the very simple case, like the gas, single phase, single component. And then as we understand the behavior of a single component, single phase, we are going to make that more complicated, adding more components. And then when we learn that, we're going to add different phases. So we start with a very simple case, and then we will build on that. Okay. So the first thing is we just need to make sure that we understand the definitions. Whenever we are talking about the phase behavior of the hydrocarbon fluids, we always uh, we always mention the pressure, temperature, and volume associated with this oil and gas. So it doesn't make sense to talk about the phases without mentioning the condition that we are going to measure these properties. Okay. So one of the major properties that we are going to work with is the pressure. Okay. So what the definition of the pressure is basically is a physical measure of number of fluid molecules present in the system and their motion. So pressure is nothing other than the number of the molecules in the system and their motion. So as we increase the number of the molecules in a unit, let's say unit volume, we are increasing the pressure in that unit volume. As we decrease the number of the molecules in that unit volume, we are basically decreasing the pressure. The temperature physical is defined as a physical measure of average kinetic energy of fluid molecules. So when we have these number of molecules, what is the energy, kinetic energy of these molecules? That defines basically the temperature. And the intermolecular forces are nothing other than the attraction and repulsion forces between the fluid molecules. So these molecules, they react, okay? And we know their interaction is proportional to their distance, okay? So when they're away, they try to attract each other. And then when they get very close, they try to repel each other. So these attraction and repulsion forces are also coming to the picture when we're talking about the phase behavior. So pressure and attractive forces tend to confine the molecules, okay? Because when we increase the pressure, which means you're increasing the number of the molecules, then the attraction forces comes to the picture, and then they try to bring these molecules together, so they're trying to confine the whole system. But the temperature and repelling forces tends to throw the molecules apart. So when we increase the temperature, we increase the kinetic energy, so their vibration and their motion becomes higher, so they get away from each other. Okay. And exactly like repelling forces, when these molecules are coming together, when they get very close, then repelling forces, they just threw them away. So we just need to remember these basic behaviors, basic definitions, and then as we go through the study of the phase behavior of these molecules, we can have a better understanding. Okay. So if pressure is increased, molecules are forced closer together so that the gas will be compressed, okay, or changed to liquid. So as we increase the pressure, which means as we increase the number of the molecules per unit volume, the intermolecular forces goes up. So it tries to confine the system, it tries to bring the molecules together, and as the molecules are coming together, they generate more denser phase. And if we keep continuing increasing the pressure, at one point every turn, the system turns to the liquid. Okay, and as we decrease the pressure, meaning that we are removing these molecules from that unit volume, then the system becomes less dense. Basically, we are decreasing the density of that system, and the molecules become far away, far apart from each other, and then the system tends to go to the gas phase. Okay. So in the gas phase, the molecules are thrown apart by their own kinetic energy and molecular repulsion. If molecules are smaller, there is less molecular attraction, and as they become bigger and bigger, then there will be a larger intermolecular forces. Okay. So generally in the liquids, we have larger molecules because they have higher intermolecular forces. Okay. And in the gas phase, we have smaller molecules, and then they have smaller intermolecular forces. Okay. So generally in the oil and gas studies, we are referring to what we call phase diagram. Okay. The phase diagram is basically the pressure-temperature relationship, okay, of a system that we are studying. Okay. So if we plot pressure versus temperature, then we are studying at what condition this system will be liquid, at what condition this system will be gas, and at what condition this system becomes solid, or at what condition both of liquid and gas will coexist. Okay. So just consider a specific mixture or a specific component. Okay, so for example, we know the component. Let's say it's methane. Okay, and this methane is not a good example because it's a gas in the conventional pressure and temperature. It can be liquid, but you have to really drop the temperature. The critical temperature of the methane is minus 116 degree Fahrenheit. So to have it as a liquid, this methane as a liquid, so the temperature has to be much lower than, let's say, butane. Okay, so if you have a butane, which is a heavier component, and this butane could be gas in a gas phase, it could be in a liquid phase, or it could be both gas and liquid coexisting. So butane as a gas and as a liquid. Okay, and this only depends on the pressure and temperature of the system. So in the phase diagram, we are studying these conditions. We wanted to know if I have a specific component, let's say pure substances, or if you have a mixture of the two components or a mixture of the multi-components, at a specific pressure and temperature of our reservoir or our operation condition, what do we have? Do we have a gas phase? Do we have a liquid phase? Or we need to deal with both in gas and liquid? Okay, so that's what we are interested in. There are cases that we can have also the solid, as I said, in the case of gas hydrates. Okay, so in the case of hydrates, you have the gas molecules trapped inside the water molecules, and then the whole system turns out to be solid gas solution. It's like ice, or it's like snow type of thing. But here for now, we are going to just focus on the right side of this phase envelope, where we have gas, liquid, and these two-phase region. Okay, so in this graph, there are a couple of definitions that we need to work on. So first off, as I said, the phase diagram refers to the pressure and temperature behavior. Okay. And then we have what we call a critical point. Okay, a critical point has a specific definition if you have a pure substances. Okay, if you have a pure component, then this critical point has a specific definition. If you have multiple components, like two components or multiple components, this definition will be different. Okay, but for now, let's look at the pure substance. As I said, first we start with the very simple case where we have only one component, and then as we go, we start adding more components, and then we're studying that behavior. Okay. So what is a critical point? So the critical point in the phase diagram is defined by critical pressure and critical temperature. The temperature associated with critical point and the pressure associated with critical point. The critical temperature is a temperature, okay, above which we cannot liquefy gas no matter how much pressure we apply. Okay, so as I said, let's say if this is methane, the critical temperature of methane is minus 116 degree Fahrenheit. So above minus 160 degree Fahrenheit, minus 116 degree Fahrenheit, no matter how much pressure we apply, we cannot liquefy methane. So therefore, methane will be gas and will stay gas in any practical conditions. Okay. So the critical temperature definition is a temperature above which we cannot liquefy gas. Okay. Critical pressure, on the other hand, is a pressure above which gas and liquid cannot coexist. Okay. So above the critical pressure, you either have liquid or you have gas. There's no way that you can have gas and liquid coexisting. Okay. And as I said, these definitions are valid only for pure substances. And then we have the vapor pressure line. Okay. The vapor pressure line is a line, basically, or it's a curve that separates the liquid phase from the gas phase. Okay. In the case of pure substances only, this region is a line, okay, or is a curve. So the only condition that we can have gas and liquid, both phases coexisting, is on this line, okay, on pressure and temperature associated with this line. Okay, if we increase a little bit of pressure, we will have liquid. If we drop the pressure, we'll have gas. Okay, only on the pressure and temperatures associated with this line we can have gas and liquid coexisting. Okay. So as I said, we are going to just consider this part of the graph where we have liquid, gas, and liquid on the vapor pressure line. Okay. I've gone through this through the definitions, but how we can find this, how we can generate this phase diagram, pressure versus temperature behavior. There are different techniques, that we can perform. In the lab, we can do the lab test on two different sets. We can do the lab on a constant temperature, or we can do the lab test on the constant pressure. Generally, in the oil and gas industry, we are doing the experiments on a constant temperature, okay? Because we assume the reservoir temperature will stay constant, and we are operating at a constant temperature, except if you do some sort of like a thermal recovery. You inject steam, you inject hot water, you do combustion, you do SAGD, you do something that changes the reservoir temperature. Otherwise, we assume that this reservoir is at a constant temperature. So the way it works is generally we will have a sample, like a pure component, and we put it in the cell, in the cylinder, and then we are using mercury to increase the pressure. Okay, so we are using hand pump, let's say, and then we inject mercury, we compress this liquid, and we increase the pressure such that we make sure this is all liquid. And then what we are going to do is we are going to drop the pressure. Okay, so we drop the pressure by removing the mercury from the cell. And as we drop the pressure, this liquid starts expanding. Okay, so we are at 0.1. And if we remove the mercury, the pressure starts dropping and the liquid starts expanding. It expands till the point that the first gas bubble comes out of the liquid. That point is defined as a bubble point. Okay, that point where the first gas phase comes out is a bubble point where we have two gas and liquid coexisting. And then if we continue removing mercury and expanding the liquid, more liquid converts to the gas while the pressure stays constant. This behavior continues till the last droplet of liquid goes to the gas phase. That's what we call dew point pressure. And after that, the whole system goes to the gas phase.